Hey, welcome back, everyone. Let's finish up our discussion of carbohydrates and talk about some reactions of simple sugars. And the great thing is, since, as we've already said, simple sugars and even larger sugars are just polyhydroxyaldehydes and polyhydroxyketones. Well, we already know how hydroxy groups behave. We've covered that in chapter 7. And we already know how aldehydes and ketones behave. We covered that just recently in chapter 9. So it's going to be the very same kinds of reactions. I don't anticipate there will be any truly new reactions here. The reagents might look a little different from something we're used to, but it's basically just an alternate way of doing the same thing. So for example, we already know that you can convert an alcohol to an ether using a Williamson ether synthesis, which is nothing other than an SN2 reaction, treating the alcohol with a strong base, and then, or at least some kind of base, and then treating it also with some alkyl halide, preferably primary, and then you get an ether as a product. Well, the same thing happens with sugars. This is one of the D-aldohexoses. I don't even know which one it is. However, I can tell you it's not glucose because we have an acyl OH group over here. It doesn't really matter. Either way, when we treat this, if we were to treat this with, let us say, an excess of 1-iodobutane, in the presence of at least some kind of base, you'd at least want a weak base like triethylamine, which this is. You could also use pyridine, which looks much like benzene, except one of the CHs is replaced with a nitrogen. I would at least want a weaker base like that. I would be afraid, though, to try something too much stronger, as I would be afraid of doing an elimination and winding up with butene, 1-butene. Another alternative that works really well is to use a silver 1 salt, like silver 1 nitrate or silver 1 oxide. That encourages the iodide ion to leave in the SN2 reaction because the resulting product then is a silver 1 halide salt. In this case, you get silver 1 iodide, AgI. And silver 1 halide salts are exceedingly insoluble. And so silver ion really, really, really likes halide ions, and they make these exceedingly insoluble precipitates. And so that's another way of doing it. But you need an alkyl halide and then some kind of base or the silver 1 salt. Either of those would be fine. And what will happen is you will then alkylate every single one of the OH groups in the sugar molecule. Here I'm using Bu as an abbreviation for the butyl group, just CH3CH2CH2CH2. You don't have to use that abbreviation if you don't like it. I just ask that when you see it, you understand what it means. I thought it would look a lot uglier if I just drew out butyl groups and all of those. But you could certainly do that. And ugly or not ugly is in the eye of the beholder, I suppose. Another reaction that you can do with alcohols is to convert them into esters. And we're going to learn more about that in chapter 10, which is coming up next. There we'll learn that if you treat an alcohol with either an acid chloride or an acid anhydride, it does not matter which. And here I'm just using acetyl chloride or acetyl anhydride as an example. I could have picked any acid chloride or any acid anhydride. Again, you will want some base present. I would use an amine base. I would use something like triethylamine or pyridine, but there are others that you could use. And in that case, you will wind up putting what we call an acyl group on every single one of the OHs. So if you used acetyl chloride or acetic anhydride, you would get acetate esters all the way around. And sometimes you'll see AC as an abbreviation for CH3C double bond O. So ACO is CH3C double bond O, and then attached to the next thing. So these would all be acetate esters if you use the acid chloride or acid anhydride of acetic acid. But you could certainly use some other acid anhydride or acid chloride, and that would also work just fine. I don't know of a way of either alkylating or acylating only a few of the OHs using either of these methods. It's basically all or none. So in the case of the alkylation reaction, we would expect all of those mechanisms to go by an SN2 mechanism, let's just say. The mechanism for forming an ester in this way is somewhat different. We'll probably learn at least a little about it in chapter 10. It's known as the nucleophilic acyl substitution. For now, suffice it to say, this reaction is neither SN1 nor SN2. It's something other than either of those. A couple other reactions of simple sugars that we already know about from aldehydes, ketones, and alcohols. We've already learned that an aldehyde or ketone functional group can be reduced with a hydride reagent. Indeed, if you treated this sugar, whatever it is, it's not glucose, because glucose is right, left, right, right, and this is right, right, left, right. So whatever that is, if you were to treat this with aqueous alcoholic sodium borohydride, followed by a dilute acid workup, just as it would with any other aldehyde, it will reduce the aldehyde functional group to a primary alcohol. And it leaves everything else untouched because there is nothing else that can be reduced. Lithium aluminum hydride would in principle also work. If I were doing it in real life, I would certainly try sodium borohydride first because it's a much less reactive and thus dangerous reagent. We can also perform oxidation reactions on the aldehyde functional group and then also on this primary alcohol. If you treat a simple sugar like this one with aqueous bromine, bromine is a good oxidizing agent. The way you can know that is because in Br2, of course, the oxidation number of the bromine is 0 because you've got a pure element, right? But we already know that bromine likes very much to be in the -1 oxidation state. In other words, as a bromide ion. So if bromine is going from 0 to -1, as it does in this reaction, it's getting reduced. And if it gets reduced, that means it's an oxidizing agent. And it's going to oxidize, in this case, quite selectively, the aldehyde functional group on an aldose to a carboxylic acid functional group. And amazingly enough, it doesn't touch anything else. None of the other OH groups gets oxidized. And compounds of this type are called aldonic acids. Not that I really care very much if you memorize that term. I always forget which is an aldonic acid and which is an aldaric acid. And so I don't see the point of making you memorize that either if I myself don't have it memorized. A slightly stronger oxidizing agent is nitric acid. And this will give off oxides of nitrogen as the byproduct, but the major organic product is what results from oxidizing the aldehyde group of an aldose and the CH2OH group, the primary alcohol group, both to carboxylic acid functional groups. This is another very useful reaction. And again, for whatever reason, interestingly enough, nitric acid doesn't touch any other OH groups that may be on the molecule, just the top and bottom functional groups. So I always thought that was rather interesting. I forgot to mention that the reduction of a sugar to, or rather the reduction of a sugar with sodium borohydride gives a type of compound known as a sugar alcohol or an alditol. And these are used quite a bit as artificial sweeteners. You can actually go to the supermarket now and buy xylitol or other similar compounds that are used as artificial sweeteners. These things also have been used for a very long time in chewing gum, is my understanding, because these alditols have two benefits. First of all, they're sweet. Second of all, the bacteria in your mouth really doesn't like sugar alcohols. So it fulfills a double purpose. So much for the redox reactions of simple sugars. Next, I'd like to talk about the formation of glycosides and also the formation of disaccharides and polysaccharides. So I'll do a little cleanup of my chalkboard, so to speak, and we'll be back in just a moment. Okay, presto changeo. Another important reaction of simple sugars, like this one, again, whatever non-glucose molecule this is the formation of what we call glycosides. And that involves a reaction only at carbon 1, or the anomeric carbon, as it's also called. That's the carbon atom that used to be the aldehyde carbonyl carbon when the molecule is in its open chain form. And it turns out that when you heat a sugar in some simple alcohol, could be just methanol or ethanol, here I'm using methanol, well, the very same thing happens as when you heat any aldehyde or ketone with a small alcohol. In this case, you'll wind up going from this hemiacetal to a full acetal. And so we go from having an OH group to an alkoxy group over here. And in this case, the alkoxy group comes all from the alcohol. And you wind up losing a molecule of water. The H from the alcohol and the OH group and the sugar essentially wind up combining to form a water molecule. And another byproduct of the reaction, you won't be responsible for the mechanism. It's a bit more complicated than the one we learned in chapter 9 when we discussed forming acetals and hemiacetals. And the reason it's more complicated is there's actually easily 2 or 3 plausible mechanisms. So we don't need to worry about the details. One of those plausible mechanisms, by the way, is similar to what we learned in chapter 9. But be that as it may, mechanism aside, even if you started out with anomerically pure sugar, in other words, this one would be, let's see, that's pointing down, so it's alpha, right? Because the consonants and vowels don't go together. So let's say you started with this sugar in the pure alpha form. After the reaction is over, you will get both alpha and beta in terms of the glycoside product. But compounds of this type are called glycosides, and they're ethers of simple sugars at only the glycosidic or anomeric carbon. None of the other OHs gets touched by this reaction. They're not able to react with the alcohol under acidic conditions, because the thing that's special about this OH group on the glycosidic or anomeric carbon is really the carbon atom here is an aldehyde in disguise. And so that's not true of any of the other OHs. So you're not going to be able to get a reaction of that type. And luckily, once one understands that, then formation of a disaccharide is the exact same thing. The only difference is, instead of maybe a small alcohol like methanol or ethanol, we'll just use any of the many OH groups on another sugar molecule. And so in the presence of either an acid catalyst, or there are also enzymes, of course, that do this for us in the cell, you wind up removing the essentially the OH group here and the hydrogen off of this OH group. And I could just as easily have used one of the other OH groups. And the enzyme, of course, will also choose whether you get the alpha or beta anomer over here. So all that is down to specific reactions in the cell. And you'll learn more about that in your biology and biochemistry classes. What's important for us here is that this type of reaction is the exact same thing as forming a glycoside of this nature, except instead of O-ethyl at the end, you've got, or O-methyl, you've got O really big molecule. But the reaction is the same, the mechanism is the same, and if you understand one, you know all you need to know in order to understand the other. And this is how disaccharides are made. And there are plenty of important disaccharides. A bunch of them are listed in particular in the book. They include sucrose, they include lactose. A lot of people are lactose intolerant. And so I don't know what this one is, because I don't even know what the two sugars are. I certainly would never expect you to memorize any particular disaccharides or polysaccharides in terms of their structure. But if you were given a structure like this, I'd expect you to understand certainly that it's a disaccharide and how a molecule like that might be made. And then you will notice that you have another anomeric OH here. And so in principle, you could bring in a third sugar molecule and do the very same thing, and a fourth, and a fifth, and a 5,000th, and so on, right? And so that's how polysaccharides are made, like starch, like glycogen, right? Things like that, like cellulose. Those are polysaccharides. Again, I would never say draw starch, I would never do that to you or expect you to recognize it out of a lineup. But if you saw the structure, I would certainly expect you to say, well, that's some polysaccharide, and it's made just by repeated formation of glycosides, bringing in one sugar at a time. And again, both the stitching together of polysaccharides and the breakdown of polysaccharides are done enzymatically. And so there are enzymes in living systems that do that for us. Good. And with that, I think we're pretty much done with chapter 16. So by the way, you will want to go on eCampus. I noticed I made some just minor typos in the class notes, so I would like to fix them. Other than that, I believe we'll be continuing on next with chapter 10. So hopefully by Monday or so, you'll find your class notes for chapter 10 ready. I will also update the syllabus then if need be, if I didn't quite figure out far in advance what our exact coverage will be, but all that will be coming along shortly. So other than that, have a good day.